Hi everyone, today I'm working through question 15 part A of the 2020 Extension 2 Sydney Boys Trial Exam. So this part A is an induction question and we're told a triomino is an L-shaped tile made up of 3 1x1 square tiles as shown below. We're then asked to use induction to prove that triominoes may be placed on a 2 to the n by 2 to the n square board in such a way that there is only ever a single 1x1 square left uncovered. And the triominoes may not overlap when you're trying to attempt that. And then we're given this hint to consider the position of the uncovered square in each inductive step. And personally, I think that hint is a very, very subtle nudge that for this induction question, drawing up graphs or charts is really going to be the way to go. We want to take a graphical approach to this as opposed to a purely algebraic approach. I suppose if the question writer wanted to be really direct, they could have said as a hint, you know, draw this up or use graphics or some kind of very direct nudge that this won't be pure algebra. So it's quite an interesting induction question from that perspective, because whilst we follow the steps of induction as we normally do, I think where a lot of students may encounter challenges with a question like this is where we're kind of stepping out of the box in a way, no pun intended there, but we're kind of having to apply what we know about induction, but just in a different way. And I think the subject matter of this question, triominoes, again adds a layer of difficulty, because I don't remember learning much about triominoes or there's these things called polyominoes, which are all the different types of arrangements of 1x1 squares. So here we've got triominoes, which involve 3 1x1 squares. You may have heard of dominoes, which involve 2 1x1 squares. So dominoes, those things that are often lined up and pushed over. You may even have heard of tetraminos, which involve 4 1x1 squares, if you've ever played the game Tetris. If you look closely, you'll notice all of the different shapes that you can deal with in Tetris involve 4 1x1 squares in different arrangements. So that's where the word Tetris comes from, tetramino. So they're kind of maybe places you may have encountered these ideas, but I don't think there's any formal teaching of it in the math curriculum at any point in high school, at least not when I went to high school. Maybe they've changed it now, but I would suspect for many students this is quite a novel subject matter, and so maybe that makes it a little bit harder again. But as we see, as long as we are careful with the way we draw up our charts, we can tackle this one without too much trouble. So yeah, let's take a look. So here I've written out what we're being asked to prove, and I've noted this hint about considering the position of the uncovered square, because I think that's our guide to say, you know, use graphics to deal with this. So let's follow the steps of induction. So step 1, as usual, is to show that it is true, what we're trying to prove is true for our first value of n. Now in our case, it will be n is equal to 1, because if we wanted to do n is equal to 0, we'd have a 2 to the 0 by 2 to the 0 board, which would be a 1x1 board which couldn't fit a triomino on it. So we're going to start with n is equal to 1. That's our first case. And so it's handy that I'm working on grid paper here, because I can just treat each little square on my grid paper as the 1x1 square. So if we got a 2x2 board, that's just going to be 1, 2, 1, 2. And if I want to shade in a triomino, I could pick this arrangement, and if I shade that in, we can see that there's only one square left uncovered. So we can say that this is true for n is equal to 1, and I think that that diagram is all you need. I don't think you need anything more than that to satisfy whoever's marking you here that you know why it's true for n is equal to 1. So then we come to step 2, which is to assume true for n is equal to some integer k, and this is where maybe diagrammatically it gets a bit trickier. I think we can still do it, kind of what we need to do is note that it's a 2 to the something by 2 to the something board. So if n is equal to k, what we're dealing with is a 2 to the k by 2 to the k board. So we know that the board will be some amount of going down and then across by 2's, we just don't know how many. So the way I'm going to represent that graphically is I'll go down 2, and then I'll just put a dot, 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 and then down another 2, and then across 2, and then a dot, 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 and then across another 2, and so on, just to kind of make it clear that I don't actually know how big this is, but what I do know is it's a square, and I do know that both the width and the height of the square is some power of 2 to the power of k in this case, for all various values of k that we might want to put in. And if we're assuming it's true for n is equal to k, what we're assuming is that we can use, we can overlay various triominoes such that there'll only be one square left uncovered. And here I'm just going to pick the top right. I could have picked any square actually, but I think the top right is not a bad idea. So just in the diagram, I'll shade in everything else to indicate this is what we're assuming. And now we get to step 3 of the induction, which is where, for most inductions, all the heavy-duty thinking happens. So here we need to show that what we want to prove is true for n is equal to k plus 1. And this is where I think this hint is going to become relevant. But before we get there, I think what we can do is think about the size of our board. So our board will be 2 to the k plus 1 by 2 to the k plus 1. That's the size of our board. Now, just doing a little simple algebra, we can say that's 2 times 2 to the k, because that's how we can deal with this k plus 1 in the exponent, by 2 times 2 to the k. And the reason that's a good idea is because often with induction you want to link step 3 to step 2. And in step 2 we had a 2 to the k by 2 to the k board. So we'd like to have 2 to the k by 2 to the k in what we're dealing with, so that we can make our link. And so here we've got 2 times 2 to the k times 2 times 2 to the k. These 2's we can bring together as just 2 times 2 is 4. And then we've got 4 of these 2 to the k by 2 to the k boards. And that 2 to the k by 2 to the k is what we've assumed true. And we've got 4 of them. So really, in terms of our diagram, if we can draw up 4 of these and link them together in some strategic way, making note of this hint, I think that's going to get us what we need. So what I might do is let's just start by drawing 4 of these 2 to the k boards. Now I won't do any shading yet because I think we want to be strategic about where we put our uncovered squares. So step 1, I'm just going to draw the 4 boards together, and then we'll think about where our uncovered squares should be later. And then just one more to go. Okay, so here we have four of our 2 to the k by 2 to the k squares. Now, I think the most strategic way to think about our uncovered squares from our 2 to the k by 2 to the k boards is to make sure they end up together. And so here I've got one in the top right, so maybe I'll keep that in the top right for this one here, so we know all of that can be covered by triominoes. But for the next one, I might, you're effectively rotating this so that the uncovered ends up in the bottom right, which maybe works for this top square. So let's say that is the one that's uncovered, and then everything else is what we cover with our triominoes. And then if I was to rotate it twice, we'd get our uncovered in the bottom left, which I think makes sense for this one. And the rest, again, we can cover, making use of our assumption in step 2. And then finally, if you rotate it, I guess you could rotate it the other way, and you'll end up with the top left being uncovered and everything else being covered by our triominoes. And the reason why that is the way to go is because we've got these 4 uncovered squares, and we're kind of back in step 1 territory where we know, maybe I'll just use a different color, we know we can shade in a triamino such that there's only one square uncovered. And when you put all that together with our n is equal to k plus 1, again, we can apply our triaminos so that everything can get covered without any overlapping except for just one square. And so therefore we can conclude, hopefully you can see this, therefore it's true for n is equal to k plus 1. And so now we can make our final conclusion, which I'll just put over here. So therefore, step 4, I'll just write by induction. You can write however you've been taught to write the inductive conclusion. I'll say by induction, and then I'll just rewrite it. So triominoes may be placed on 2 to the n by 2 to the n board. So there is only ever one square uncovered.
Sonic boom!
And I reckon that's it for that question. So as I mentioned, it's a little bit different. I quite like this question because the question writer is really testing a student's ability to apply induction in unfamiliar contexts and in unfamiliar ways. I mean, the unfamiliar context are these polyaminos, in this case a triamino, but the unfamiliar approach is very much a diagrammatic technique that we need. And there was a little bit of algebra there, but not a lot. I mean, in most of the induction questions you tackle, it's mostly algebra. Step 3 is really testing, do you know all the techniques required to simplify things, typically algebraically. But here it's totally different. It's almost just pure logic and thinking visually. And yeah, I can see why plenty of students might struggle with a question like this because they probably just haven't practiced questions like this before. So hopefully seeing me work through this helps you get a feel for how you can think about something like this and give you a little bit of practice. I suppose you could go and search online for more questions like this to get a bit more practice if you're concerned you may encounter something like this again on a high stakes exam like the final HSC. But yeah, hopefully you see it's actually not overly complex. It's pretty simple. You just got to be careful and methodical about what you're doing. So yeah, there you have it, and tick boom.